Any more questions from, we actually have, we can stick around. There's actually a design of this workshop is to have a few, time, at least a half hour for participants to ask question, discussion, anything related to my, doesn't have to be limited to my talk, also can be, questions for Professor Yu. Any more from the audience? Yeah. Questions? Oh, there's someone at the chat room. In polar coordinates, feature depend on the center. Is that true? If so, how do they select? Oh, good. That's actually a good question. So in our case, we actually assume that we only, as I said, the setting is still very, we're considering the rotation and the translation separately, right? In the future, we'll combine them. We're not considering all the digits supposed to be aligned in the center. So just take the MNIST, I mean, take the image center and rotate it and build the multi-channel signal. We are not handling translation and rotation simultaneously yet. Yeah, if that answers your questions. But definitely it's interesting, how do we build those together? Now we have the more general principle. How can we, the larger groups, as I pointed out in my question, I'm sorry, direction for future work is how do we extend the same frameworks to more diverse groups? Yeah. There's also, there are a couple questions on the YouTube live stream. Can I read? Yeah, sure. Can you please? Yeah, Larry says there's some more questions on the YouTube live. Are ML-trained DNA classifier also more robust to certain input corruption? Do they have the same? So that's a great question. So we actually, the first author of the paper was Yaodong Yu. I think he's actually still the defending champion of the adversarial training work. First we tested on this MCR trained DNA. We tested the robustness to the input. It's not, but it's not worse than other network, but it's not better. So that actually gave us more reason to believe. And the long robustness comes from the network structure, the ReNU network, the residual network, not from the object function. So we tested on the new data sets, new architecture, the ReNU network. So at least for the vector case, we do see the resulting network is more robust because every layer is natural, right? It's also smooth. But again, we're at a very early stage. We're not really testing, on the ReNU networks, or even the design is still very basic, as I pointed out, right? So that is really for future work. But now we're kind of confident that is really the long robustness comes from the selection of the network architecture, right? Because there's things we don't understand about those existing networks. And there's also one from, if that answers your question, in Wang, I'll read the question. Seems that the structure and theory can support expanding the existing network. For example, can the 0-1 classifier easily expand to support discriminant 0-1-2? What's your, well, of course, as I said, doesn't stop you to run more classes, more data, more environments, but there is a computation cost to go with it, right? So indeed, right now we're building this network with considering with all shifted or rotated as the training, right? Building the discriminator or the expansion or the compression terms. So if you have computational resource, let's go forward, right? By the way, I actually think that this opens up for more demanding of computational resources, especially if once you start to extending this to unsupervised learning setting, and also taking care of more principled way of handling all the environments. This does, but it scales gracefully. So to be sure, right? At least I believe that this method scales gracefully. Second, it starts to provide guarantees. Every stage you're building a network, every stage you're training a network, every component is perfectly meaningful to you. Something goes wrong, you can find out, right? If it's not compressing right, if it's not expanding right, it's immediately. That's what we found out very nicely with this framework. By just monitoring each of those rates, how they grow, how they reduce, you actually can say if even your implementation is right or wrong, right? So you have some physically or statistically meaningful quantity to monitor throughout the training process, throughout the building process, by the way. Another thing I wanted to point out is also some of my students working on naturally. See, from the optimization point of view, right? We run 3,000 layers, iterations, fine. But in reality, you don't have to, right? Remember, there's a paper by Yang LeCun, right? So the mention, Lista. So even for sparse coding, we don't have to run the optimization to the death, right? You can stop at the, let's say, 50 layers iterations. Then what you can do, you can backpropagate. You can retrain the network, right? You already, so this forward building process already gave you the nominal direction, nominal trajectory. All you have to do some moderation. So the whole backpropagation is really fine-tune the network. There's nothing mysterious about it anymore, right? So we have been doing that in optimal control for years, right? Called the finite horizon model predictive control, right? We solved the optimal control problem, right? So we optimize the trajectory path around the nominal path. So then, at least for now, in this framework, everything we do very much in neural networks so far has a perfect explanation. How does the principle cover structures like LSTM deal with sequential? Great, that's one of the open problem, right? I listed there. Excellent. So if, I'm more thinking about, let's say, if we're dealing with future, we're dealing with system ID, right? The data as a dynamic data will have internal structure as well. In addition to the shift invariance, in addition, so far we only consider the very basic structure, the data as vector or data as a shift invariant sets, right? So, but in the future, of course, the data, if it comes from a dynamical system, right, such as speech or from some driving or optimal control problem, how those dynamic structure gets embedded, collaborated with this framework, it's a great story. Again, also we know because of dynamic setting, right? If you have a linear system and so on, the data, the observation will have low dimensional structure. If your system is linear, we know even the underlying structure is linear. You don't have to do on nonlinearity. So you only have to group them well, identify each of the subspace correctly. So there's a lot of things we can do. By the way, right now it's all kinds of projections you can go from here. But at least I think that again, the principles of compression, that you really have to be clear what you are gaining by paying every ounce of your computation. That's really what I believe for now. By the way, the whole work, the reason we looked at this work is actually from a discussion we did with Yang LeCun. He was also interested. I think even before the deep learning revival, he was looking at a really precisely sort of energy approach. What is really deep network is trying to optimize, right? He's searching for, he even have a Europe's workshop about that, right? What is the proper energy function that the neural network is trying to minimize? And something similar from say physics, right? Thermal or kinetic or potential energy. So we had a discussion. So, but I at the time, I believe it's really the measure, some information theoretical measure. And he was believing some maybe physical inspired energy term. Or sparsity dimension, we agree on that. But regardless, right, the point is that really you want to know by every layer or by every backpropagation, really what you are optimizing, right, rather than just fitting the labels. So again, I mean, a lot of this work are kind of still preliminary. We're really excited how we can take on, just like Professor Bingyi has said, take on to real world scale performance and so on. And also there's really from the, as I said in my talk, right, there's open product directions in the theory side, on the architecture side, how to make this more scalable. For example, right now, just from the shift environment, the reason why Bingyi is not very, still the computation is expensive is that, say from the duration, each multi-channel convolution, we still just have the generic convolution, meaning that the support can be as large as the image, can be as large as the whole span of the temporal domain. But then what are the question, how, as I pointed out, right? If you assume, if you are, let's say dictionary are sparse and short, John Wright has done a lot of analysis on that, right? If the data are compositional or hierarchically compositional, can we prove the filter, each convolution, the multi-channel convolution naturally converge to very spatially localized filters? That's completely open. If that is true, then we will be very, very safe to just using spatially localized filters each layer. We will definitely scale, right? So one of the comparison with ResNet, you can see that they're using very, very 3 by 3, right, 5 by 5. Here, our layer, each ENC is a big convolution. It's a convolution, but it's a big convolution. If that also answers some of Professor Bingyu's question. Not yet, the slides, but the talk will be, and someone asked if the slides will be available on the internet. I will basically, I think the talk will be recorded, and the CDTI is doing a great job. They were going to edit our talk very professionally and then put on the internet. So you should be able to have this, the talk. Maybe at some point I'll probably release. Some of the work is still under submission. I don't know if we are, maybe we can release that a little bit later. Thanks for asking. The funny thing is that actually we derived this object function is trying to do truly unsupervised learning and not really, our initial goal is not actually try to understand the deep learning or at least not the purely supervised setting. In fact, I don't think the supervised setting does its justice, to be honest, right? It's really it's sort of a more general principle to govern how should we organize data, regardless of how they are labeled, right?
Yeah,
go ahead.
Yeah, you were pretty fast. For all the formulas, did you have to assume it's a Gaussian mixture?
Yes, so exactly. So there are two things. Yes, the rate reduction, as just the Gita mentioned now, right? The rate distortion function is not very computable for many distributions. It's very hard to compute. However, fortunately, two types of distribution, Gaussian or degenerate Gaussian or subspace. That formula gives the uniform bound and very, very tight. Even the Gaussian can be degenerate, or even the data just have a subspace-like distribution. It doesn't have to be Gaussian. As long as it has a subspace-like distribution, it actually is give a very tight upper bound from our experiences.
Yeah, so that's great. You can get analytical formula.
Yes. And another thing to answer your question is that one thing you don't have to, if you have a nonlinear distribution, you don't have to, as long as you believe there's a kernel trick. Actually, in our original minimal incremental coding length paper, we actually played the kernel trick. Just so you as long as you believe certain kernel can make your data more like subspace or Gaussian, you can apply that because naturally you just replace the inner product in that. We actually replaced that in the classification setting. It works actually pretty well. At the time, already beat the LERLET, the convolution network, just by having a kernel and with the compression. We never go very far with it. Again, the reason is that the classifier we get is long parametric, right? You have to use, every time you classify, you compute the volume with the difference of volume with all the data. But the principle wise, it's actually pretty magical. See how it works so well. So if you have a long Gaussian structure, one, you can try to get an analytic form, or you can use a kernel trick. That's currently the state.
You need some separability.
Yes.
Otherwise, sometimes if it doesn't separate in the kernel space, then the approximation and then. So
yes.
Do you get exactly the same algorithm? You get more or less the same algorithm.
No, so that's where really that interesting part about the sparsity comes in, right? I mean, people didn't realize, right? All the modern neural networks, before they hit ResNet, right? What they do, uniformly, you're lifting everything, multi-channel, right? In fact, that layer is not, in many cases, you don't have to train. Just use a random layer, enough number of random kernels and the hitting. So now it's actually become very, very clear. Why, especially you strive for invariance and so on, right? If you want to separate your signals at all possible locations or augmented data in the shifted version, then that you really have to count on the first few layers of features are somewhat separable already. And the rest of the network will be coached to separate them better, to select the features and also push them apart.
So what's the answer to the question? Do you get exactly the same algorithm or you get approximately the same algorithm?
No, you will get different algorithm. There are places you need to design, right? So for example, if you use different filters for encouraging sparsity to make your data more separable and so on, right? Yeah. Or you can actively learn a dictionary. So that will change at least the first pre-processing of your data. But the point is that once you, under the assumption that the pre-processed data, the sparse codes, the multi-channel sparse codes are separable in general, binarily separable, and the Redu network will just do the job, right? So everything becomes fully autonomous from then on. There is a very, I don't want to do this, but there's my colleague John Wright, who is a co-author on this. He has a humongous paper recently, just to show you how hard just to mathematically prove using deep network to separate two manifolds. He actually has a paper called multiple manifolds, deep network multiple manifolds, showing that characterize what conditions on the manifolds in terms of curvature or distance and the correlation, so that you can guarantee that the network with a tractable layer, tractable polynomial number of layers or width, you can guarantee that you can train a classifiers that certifiably correct, give you the classification results. But that's again very preliminary on the binary classification problem. But just to show you how hard it is, just to characterize and what conditions on those initial manifolds in order for the rest of the classifier to guarantee to work. So far, considering that part still purely empirical, right? We construct a Redu, we chose 5 channel that happens to work. We can choose 10, but if we have more faster computers, people these days, Google, they use 1,000, right? We can use 4 or 5, but anyway. So you verify the concept, but whether or not this Redu, this unrolling algorithm architecture guarantee to give you the classification, no, there's absolutely no. Just like we have a nonlinear object function, we run a greedy descent, there's no guarantee we can find a global optimal, right? It's the same problem exists. So, but the good thing is that we can ask exactly the same questions now as everybody asking optimization in statistics, right? So the same question we had, or open problem, whatever, we have about the long convex optimization, how to guarantee convergence, how to guarantee efficiency. They completely translate over exactly to this setting. How can we get the algorithm, even layers, to be more efficient, right? So people use, people do the skip connections, right? Cross layer. It turns out, if you think about the optimization, that's exactly what acceleration is doing, cross layers, cross iterations, so on. So how to make the optimization more efficient, layers more efficient, and also how to guarantee the convergence, converge to not a local minima, but also global minima. I think Renee has given a wonderful talk or tutorial on that. There's a lot of development from purely optimization point of view to certify conditions that give you guaranteed optimality, global or local optimality.
But you do also need assumptions, right? You need ID data.
Exactly. So that's why we are trying to clarify those assumptions, right? So that's the point. We're really trying to clarify the assumption that we can make things work.
Respond 100% guarantee in practice because all the assumptions might be violated.
Yes.
Yeah, but it can be very insightful.
Yeah. All right, guys. Any more question from the audience? We have probably a few more minutes. Again, as I said, the material, I think CDTI will probably take a few days, but they will put a lot of the whole, maybe after the whole workshop, I mean, they will do a wholesale the slide presentations, probably release on YouTube and so on. So, and you are welcome to also, there's a Friday, there's actually a specifically designed whole day event on brainstorming. I really wish you can join. We will specifically dive in more about open problems. And there'll be 3 sessions, one on the architecture, one on robustness, one on fairness, So we will basically, the goal is there is not for people to talk about what they have done. It's really for people to talk about what yet to be done, right? What are really the next year or next 3 years? What are really the open, well-defined problems that we can take on for the next steps? So that will inspire more discussions. And in the end, we also hope that we will have a report of some sort, maybe some summary from the talks, as well as report from those brainstorm sessions, build up a more forward-looking tone. One thing I realized is that from this work, right, this is a big, gigantic pixel puzzle. Already you can see this, by explaining this touch upon several things: optimization, sparse representation, and also deep networks, or even harmonic analysis. Honestly, I feel sometimes very often feel inadequate to really give an answer to many of the questions. It really requires probably a group like yours. We have this two Simon's NSF Foundation team. Really, it will take a huge team effort to address some of the theoretical, algorithmic, and also application. Personally, I'm very, very eager to see some connection to. I have a joint grant with Jack Allen on the brain understanding, brain and navigation aspect. I really wanted to know if something we can either help explain what brain does, or inspired by the brain, then give us some ideas to develop better algorithms systems. Right. I always think that's very, very valuable, right? To get tested.
Right now, I think you probably start working with Jack. I'm kind of moving away from on the medical front. So
okay. Yeah.
But just still talk to Jack. But I mean, what data you'll be working with him on? fMRI data?
Yeah, it's MFI data on the human navigation. We will really try to understand perception and decision making, and also the human brain activity. How they're but the granularity is a little bit too big. But we'll see what we can get out of the data. Basically, they can monitor the whole brain at I think several millimeter accuracy. But we're trying to really
have a simulator.
Yeah,
we have somebody driving a car in.
Yes, so we have monitoring the brain, and while we're driving the car in the city, in a simulated environment. And Claire is really trying to study how people making decisions. I'm also working how people making maps, location, or subsequently, how they perceive, what information they perceive in the 2D, 3D, and a dynamical scene, right? So that's just a tons of mystery. We don't know how human does it so effortlessly, right?
There's also a culture aspect, which would be very difficult.
Yeah, we are still getting a lot of that. Yeah, very, very different mentality, people working.
Is this the proposal, the NSF Science Technology Center, or it's already awarded?
It's ONR. It's ONR project. We're trying to more on the New York Times. Jack was the lead. So, but it's good. I mean, we really, start to really thinking. There are some collections now. I think that even deep networks, also the role of sparsity, right, always plays such a fundamental role in nature, and we just still don't know how yet. But there's evidences and phenomena. I think we see similar things in the deep learning now, in the learning, side, on the mathematical side.
Yeah, I think you have to find the right representation before you know what's the right sparsity. So it's kind of a chicken egg thing.
Yeah. So that's true. That you can see that's already gets incorporated a little bit in this MCR objective, right? So how do you cluster data? Then that affects the representation, and vice versa. Representation will affect your clustering. How do you group which data is close? So on. It's already there. There's a chicken egg or mini-max kind of tension there, balance or trade-off there.
And also brain is plastic, right? So we can also have different representation for different tasks, depends on the attention. So that makes things even more complex because it's plastic.
Yes, exactly. We're aged from there, but But I think but I still believe that even brain, no matter how complicated, right? The more complicated organism probably governed by a very simple principle. I still has that belief, right? They must operate at least the parsimony or economy. I mean, this is definitely governs, right? The simplicity and the economy, right? The saving, energy saving.
I like to believe that.
Yeah.
But not always. I don't think it's always. But I like simplicity too. But it's like not simpler. That's the hard part.
Yeah, exactly. That's what we strive for.